To calculate probabilities, we first need to learn to count. In this lecture, we'll learn how to do combinatorics, deal with permutations and combinations of objects, and this will tell us how big the sample space is and how many times a particular event can happen, which means then that we will be able to calculate the probability. We will also learn in this lecture how to calculate conditional probabilities. So these are compound events. These are events in which something already has happened and we want to know the chance of something else happening. And this is very, very important. It's important in process control, in engineering, in, practically everything. It's not very hard. We'll have to learn how to deal with sets, but that's easy. And so let's begin. The factorial function is very important in many branches of mathematics, so let's begin with that. As an example, 5 with an exclamation mark, this is to be understood as 5 factorial. It means you start with 5, decrease by 1, then another 1, then another 1, and you stop at 1. So it's 5 into 4 into 3 into 2 into 1, and of course that's the same as 5 into 4 factorial. 4 factorial is this, 4 into 3 into 2 into 1. In general, you will define n factorial as n into 1 less into 2 less, and will keep going until 1. This definition then gives us the property that n factorial is n, like above, into n minus 1 factorial. So that is a consequence of the above definition. Of course, this is only defined provided that n is 1, 2, 3, 4, 5, etc. It is not defined for n equal to 0. We'll see later how we define it for that. Just for a little practice, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 4 into 3 factorial, which is 24, 5 factorial is 5 into 24, which is 120, 6 factorial is 6 into 120, and that's 720. You can see how rapidly this is growing from 1 to 2 to 6 to 24 to 120 to 720, and if we go to 15 factorial, that's a huge, huge number. If we go to a large enough n, something like, let's say, 1,000 or more, then there'll be so many digits that no computer in the world will be able to hold them. However, it is fairly easy to find an approximation for large n. It's called Stirling's approximation. This says that for large enough n, n factorial is square root of 2 pi n, and then n divided by the exponential, so this e is 2.713, etc., this raised to the power n. So that's a huge, huge number, because whenever you raise to a large power some number which is bigger than 1, then you get something that is huge. Stirling's approximation is useful when one deals with something like, let's say, a gas which has got billions and billions of atoms. We'll now define something called the binomial coefficient. It's written n, m, and the definition is that it's equal to n factorial divided by m factorial into n minus m factorial. The binomial coefficient is also called n choose m, and we'll see the reason for that later. The older notation is this, NCM, and sometimes this n is placed over here, but in most books, now this is the notation that is used. Let's look at some particular values, starting with m equal to n. And now straight away we run into a kind of a problem because we have n factorial over n factorial and then n minus n factorial, that's 0 factorial. But then we haven't yet defined what 0 factorial is. We'll do that very soon. But there's no problem if here instead of n we have n minus 1. Well, that's just n factorial over 1 factorial into n minus 1 factorial, and that's simply equal to n. Similarly, n minus 2 is half n into n minus 1. In this way, we can figure out the numerical values of all the binomial coefficients. It's just a matter of doing multiplications and divisions. The binomial coefficients that we just defined occur in Pascal's triangle. Pascal was a mathematician who lived something like 400 years ago. Incidentally, in Iran, this is called Khayyam's triangle because it's associated with Omar Khayyam, who lived 600 years before Pascal. Here's the idea behind it. So let's start with a plus b, raise it to the power 0. Well, that's just equal to 1. A plus b to the power 1 is simply a plus b. Now, if you multiply a plus b with a plus b, you get a plus b squared, which is a squared plus 2ab plus b squared. Now, you multiply this with a plus b, and you'll get a cubed plus 3a squared b plus 3ab squared plus b cubed. And if you keep doing this for 4 and 5, here's what you will get. For 4, you will get this. So the coefficients are 1, 4, 6, 4, 1. And note over here that the total powers must add up to 4. So it's a to the power 4, and then 3 plus 1, and then 2 plus 2, and then 1 plus 3, and then 4 plus 0. And similarly over here. Now if you write all these coefficients down, so let me take the last row over here. There's 1, 5, 10, 10, 5, 1. That's written down over here. 1, 5, 10, 10, 5, 1. And you can check any one of these. So the one above it is 1, 4, 6, 4, 1. And it all ends up with 1s being over here on one side of the triangle and 1s being on the other side of the triangle, and then the other numbers being below. Let's take this last row over here, and I'm now going to show you that these are actually the binomial coefficients. 5, 4 is 5 factorial over 1 into 4 factorial, that's 5. 5, 3 is 5 factorial over 2 factorial into 3 factorial, that's 10. 5, 2 is the same, 10. 5, 1 is 5. And of course, we are left with 5, 0 and 5, 1. So if we want 5, 5 to be 1 and 5, 0 to be 1, then we should better define 0 factorial as 1. Remember, it was a matter of choice. We could have defined 0 factorial to be something else, but if we want all these numbers over here and all these numbers over here to be 1, then, of course, this is the proper way to define 0 factorial. Here's something that's rather interesting. In Pascal's triangle, each number is the sum of the two numbers which are directly above it. This can be proved very easily from the very definition itself. Do try it. Here's the formal statement of the binomial theorem. It says that x plus y, well, earlier I said a plus b, but same thing, x plus y to the power n can be expanded in a series with these binomial coefficients a0, a1, a2, etc. And this ak is n choose k, which is this. How do you prove this theorem? You simply use the method of induction. You assume that it's true for n, and then you show that it's true for n plus 1. Many interesting relations can be derived. One obvious one comes from putting x equal to 1 and y equal to 1 over here. So you have 1 plus 1 to the power n, that's 2 to the power n. And so this a0, which is this, a1, which is this, the sum of all these then adds up to 2 to the power n. Many other such relations can also be derived. In calculating probabilities, we will need to know how to count outcomes. For this, we'll have to develop some principles. Let's call the first principle multiplication principle 1. Here I have a number of differently colored balls and the same number of sockets into which these balls are to be placed. So let's start with something that's easy, just 3 balls. Well, I can take the first ball and put it into the first socket over here, put the second ball into the second socket, and the third into the third, and so I get this possibility. But then I can get this, 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 and this. So I have a total of 6 different ways in which I can put these 3 into these 3 sockets. Of course, you can't keep drawing pictures, so how do you do this without that? Well, here's how you do it. You take the first ball, and it can go into this, or this, or this. That means there are 3 possibilities for the first, but then you've used up one of these 3 spaces, and so there are only 2 spaces left. So the first can go into one or into the other, and there's no choice left for the last one. So then, without drawing any pictures, I have 3 into 2 into 1, that's 3 factorial. Now suppose I don't have 3, I have n slots and n balls. Then the number of combinations can be calculated in the following way, that the first ball can go into n different places. That leaves n minus 1 for the second ball, n minus 2 for the third ball, until all the balls are used up and all the sockets are full. So that's n into n minus 1 into n minus 2, etc., and that's n factorial. Now suppose that these balls over here, n of them, all had the same color. Well, then I would have only one possibility. In other words, this n factorial would have to be divided by n factorial itself. That's because these balls have n factorial different ways in which they can be selected, and if they're all the same, well, then we've overcounted and must divide by n factorial. So that's a simple enough principle. Here's another principle that's also quite obvious. Suppose that we have n symbols. You could think of them as n differently colored balls, but now there is no limit upon how many balls of the same color that you have. Well, the claim is that given n symbols, the number of sequences of length k is n to the power k. Here's what I mean by that. I have 4 different symbols. They could be balls, they could be alphabets, they could be different kinds of fruit, and we need to create sequences that are 3 long. 3 boxes, 3 slots, 3 positions, or whatever. So n symbols, and the length of the sequence is k. In that case, this answer is obvious. It's n into n into n k times. That's n to the power k. What's the difference between the first principle and the second principle? In the first case, the number of symbols was equal to the length of the sequence. So we had 3 and 3. In the second case, there is no limit to the number of symbols. We only are told that they are of n different kinds. A third commonly encountered situation leads to what I will call the multiplication principle number 3. So suppose that we have a number of different colored balls, and these are to be put into slots. There are more slots than there are balls, and we want to know how many different combinations there are. Well, that's easily done. The first ball can be put here. That means that there are 4 empty spaces left. Then we can put this ball into one of those 4 empty spaces. That means there are 3 left. And this last ball can be put into any one of those 3 empty spaces. So the total number of different combinations that are possible are 5 into 4 into 3. And that, of course, is 5 factorial divided by 2 factorial. That's because we could multiply by 2 into 1 in the numerator and divide it by that same number. So that's 5 factorial over 2 factorial. So this is for 3 balls of different colors. But what if those balls have the same color? Well, then we've overcounted by 3 factorial combinations, so we must divide by 3 factorial. And now imagine that we have n such slots and m such differently colored balls. Well, then, in that case, the number of combinations will be n into n minus 1 into n minus 2, and then we will stop when all those balls are used up. So this is the number of different combinations, which you can write as n factorial divided by n minus m factorial. Again, that's because on this side, 1 multiplied by n minus m factorial divided by the same, and so the numerator became n factorial and the denominator remained this. To carry this one step further, suppose that the balls have the same color, in which case you would divide by m factorial to get this. N factorial over m factorial into n minus m factorial, which we call n choose m. So we had n slots, m balls, now all of the same color, and this over here is what we call n choose m. Or to put it this way, the number of subsets with m elements from a set with n elements is this. Equivalently, the number of sequences of length k from a set with n elements is this. Now, there's no point in remembering these statements. I think the best way is that in working out problems, you should remember principles, not the formulae themselves. So let's work out one particular example. Suppose we have 4 red boxes, 5 green boxes, and 3 yellow boxes, and these are placed randomly side by side with each other. What is the probability that all boxes are grouped by the same color? To be more explicit, we are asking what is the probability that we will get, let's say, red all together, the greens all together, and the yellows all together. But of course, it could be yellow, green, red, and all other combinations of that. They all have to be together. So, the solution is the following. These 12 boxes are to be placed side by side, and so by the first rule that we discuss, there are 12 factorial different outcomes. Now we could have red, green, yellow, or yellow, red, green, or whatever, and so there are 3 different ways for R, G, Y. There are 4 red boxes, and so therefore 4 factorial different ways. For green, 5 factorial different ways, and for y 3 factorial different ways. So now if we want to calculate the probability, let's remember that the probability, as we defined earlier, is the number of ways that an event can occur divided by the number of elements in the sample space, that is to say, the total number of possibilities. So what we have is 3 factorial from arranging red, green, yellow, and then 4 factorial, 5 factorial, 3 factorial, and then divide by the number in the sample space, which is 12 factorial. If you just work this out, that's 1 over 4620, and that says that the probability is going to be this. So if this random experiment is done 10,000 times, then in 2 of those 10,000 times, you will find that all the reds are together, all the greens are together, and all the yellows are together. Let's now go on to something new, the concept of conditional probability. So suppose that some event B has occurred, and thereafter an event A occurs. Then P, written in this way, is called the conditional probability. So if B has already occurred, then what is the probability that A will occur? The easiest way to think about this is that the conditional probability is just the ordinary probability with B, with the set B having replaced the sample space S. In terms of a Venn diagram, here's how to look at it. Here is the set B. This is the intersection of the set A with B. So clearly, A intersection B must lie within B and also must be an element of A. So we are asking for the probability of events that lie within this part over here, and then divide by the probability of events that lie within B. Or we can put it this way. The conditional probability is to be calculated from the number of ways that A can occur given B divided by the number of elements in B. From here, we obviously understand the following, that event A is independent of event B if the probability of A and B occurring is simply the product of their probabilities. In other words, A has got nothing to do with B and B has got nothing to do with A. And obviously this means that this over here is simply equal to PA. A will occur with the same probability irrespective of B. And correspondingly over here, that this quantity is equal to PB, it doesn't matter that A has occurred. Armed with this definition for conditional probability, we can establish a number of other truths as well. So consider this question. Given the probability of A given B, what is the probability of B given A? I remind you that this is the definition of A given B, and that's just the probability of A intersection B divided by the probability of event B. Okay, so that makes it very easy to answer because we know that A intersection B and B intersection A are exactly the same and therefore their probabilities are the same. So look over here, we have the probability of A intersection B is just this multiplied by P of B. But now interchange A and B over here, and so we get this obvious relation. And now we can calculate from this the probability of B given A. It's simply this divided by P of A. Let's now turn to another problem. Suppose A and C are disjoint events, which means that they have no elements in common. We are asked to show that the probability of A union C given B is equal to the sum of the probabilities. For this, it is best to make a Venn diagram. In this Venn diagram, you can see that this is the set A, and this is the set C, and they have no elements in common with each other, but they do have elements in common with B. The elements that are common between A and B are here. The elements that are common between B and C are here. So B intersection C here, A intersection B here. Now let's go to the definition of what's over here. By definition, we see that this is the probability of A union C intersection B. And then we have to divide by the probability of B. Now let's ask, what is this region over here? A union C intersection B. Well, obviously, all the elements have to belong to either A or C and to B as well. So it's this part over here and this part over here. These are two disjoint sets. A intersection B and B intersection C have no elements in common with each other. I think you will agree with me that these two regions can be also written as A intersection B union C intersection B, or I could have written it B intersection C, same thing. And you can see that there's absolutely no difference between this and this. But the advantage is that now we have this explicitly in the form of two non-overlapping sets, and so therefore, by the postulates of probability theory, I think I called it postulate 2 in the last lecture, well, then we have this over here equal to this plus this. And of course, we divide by P of B. But then you will have recognized that this is exactly what we have called P of A given B, and this is exactly what we called P of C given B. And so we've established a non-trivial relation which says that this probability is equal to this. Let's now work out an example of conditional probability. So suppose that two dice are rolled simultaneously. We are asked, what is the probability that a 6 will occur given that the sum of the two is 10? Let's count the possibilities. A is by definition the set of events in which a 6 occurs on either one of the two dice. So we could have 6, 1, all the way up till 6, 6, or we could have 1, 6, 2, 6, all the way up till 5, 6. Of course, one should be careful about not overcounting because you can't have 6, 6 over here. That's already included over here. Now, B is the set of events whose sum is 10. So let's ask how that is possible. You can have 4, 6, 5, 5, or 6, 4. The intersection of A with B, that is to say the elements which are common to A and to B, are then 4, 6 and 6, 4 only. That's because a 6 has to occur and the sum has to be 10. Well, then the probability of A given B is then, by definition, this probability divided by P of B, and that's 2 out of 36, whereas the possibility of B is 3 out of 36. And so the answer then is obviously 2/3. This is a clear and obvious way of working out problems on conditional probability. Let's now take another example. Of 25 batteries in a box, 10 are bad. Suppose the first battery pulled out is bad. What is the chance that the second battery is also bad? So clearly, here we have a condition. So let's see how this can be worked out. A, let's call as the set of events where the first battery is bad, and since we know that 10 are bad. That probability is 10 out of 25. Now B is the later set of events, with the second one being bad. Since the first battery was bad, there are now 9 batteries which are bad and 24 batteries that are left in the box. And so therefore the probability of B given A is 9 out of 24. Now using the definition of conditional probability, we can ask what is the probability of A and B? That is, the first battery is bad and the second battery is bad. So that's just the product of the two. 10 over 25 into 9 over 24, which is 3 over 20. Let's try to understand this and a little bit more in terms of a diagram. So, at the very beginning, we had 10 bad batteries, a total of 25 batteries, and if 10 are bad, then 15 are good, then the probability of a good battery being pulled out at the very first try is 15 over 25. And of course, 15 over 25 and 10 over 25 add up to 1. Now we've changed the number of batteries. So now in a second try, the probability of getting a bad battery is 3 over 20. Correspondingly, the probability of getting a good battery is 17 over 20. And now you can see how this can be continued on and on until all the bad batteries have been pulled out. After that, of course, the probability of getting a bad battery will be 0. The previous example tells us that it might be useful to think in terms of a probability tree whenever there is a sequence of events. So let's start with this definition that we are going to write in the following form. So you will recognize that I've simply written the probability of B given A, and I've expressed it in this form. So this is telling us that the probability of A and B, or A intersection B, is equal to this over here, and we'll represent this in the following form. So P of A intersection B, this is equal to P of A, so the probability of A coming in, multiplied by the conditional probability of B given A. Let's now ask how to get to the next level. So in this case, we will use the definition of C given A intersection B, or B intersection A, same thing, which is equal to the probability of C intersection B intersection A divided by the probability of B intersection A. From this, we arrive at this. All I have done is substituted this over here, and now we know how to go to the next branch. So P of A and B and C is equal to this. Now let's represent this in terms of a diagram. So you see, what we've done is we've gone from here to here as above, and then gone to the next stage. So now we know that the probability of A intersection B intersection C is equal to the probability of A into the conditional probability of B given A into the conditional probability of C given B intersection A. Now the rule is very obvious. We can go to the first, second, third, fourth, fifth, any number of levels. All we need to do is repeat the step above, and we will find, for example, that this over here is this thing. So you see, it's very systematic. It's the probabilities all multiplied together in a very definite sequence. And you can see that this pattern can be extended indefinitely. So it's a very beautiful example of how you establish a pattern and then you extend it further and further to any level. Let's use the idea of a probability tree to work out some examples. So suppose there's a box which has got 7 red balls and 5 yellow balls. I randomly pick one. I find it to be red and then remove it. What is the chance of finding red on the second draw? Clearly, I had 12 balls to begin with, and so the probability of finding a red ball was 7/12. And that's now to be depicted here. So at the first level, there's a probability 7/12 of a red ball and 5/12 of finding a yellow ball. Now I take out one more ball. Well, of course, now there are 11 balls left in total and only 6 red balls, so the probability of finding a red ball on the second draw will be 6/11. Correspondingly, the probability of finding a yellow ball will be 5/11 because I have not taken out any yellow ball. Now let's work out the lower part of the probability tree. So suppose I had found a yellow ball. In that case, then you can see that the probability of finding a red ball on the second draw would be 7/11 because one ball had turned out to be yellow and there's only 11 balls left, and correspondingly the probability on the second draw of finding a yellow ball would be 4/11 because there are only 4 yellow balls left and a total of 11. We can go to the third level, in which case we will have 5/10 here because there are only 5 red balls left and a total of 10. And now you can see that that is 5/10 and this is 5/10, 5/10. Now you can see that this is 6/10, 4/10, 7/10, 3/10. Now let's ask, what is the probability that on the first, second, and third draw I will find red each time? So then I will just multiply these probabilities together. 7/12 into 6/11 into 5/10. What's the probability of red on the first, yellow on the second, yellow on the third? Well, then let's follow this tree over here. So it's 7/12, then 5/11 for yellow, and then again, because we are to get yellow, 5/10. And finally, what would be the probability of finding yellow, yellow, yellow? So that's clear enough. That's 5/12 into 4/11 into 3/10. And so that's what we have over here. This tells us that the idea of a probability tree is very useful because the probabilities keep changing as the set keeps changing. Finally, I will discuss Bayes' rule, which essentially summarizes what we've been talking about for conditional probabilities. So, suppose A1, A2 up till AN are disjoint events that form a partition of the sample space S. That is to say, these sets have no overlap with each other, they are disjoint. Then, for any event B, we have that the probability of A, any one of these, A1 up till AN, given B, is equal to the probability of that A times this conditional probability divided by P of B. Now, that is perfectly obvious because if I take PB on this side over here, then by the definition of conditional probability, this is just the probability of AI intersection B, but then that's exactly the same as the probability of B intersection AI. We've seen this before. Anyway, that's not the main part of Bayes' rule. The next part is, so the numerator is of course exactly the same as over here, But the total probability, P of B, is the sum of these probabilities in the denominator. To understand this better, let's use a Venn diagram and take a particular example. From that example, we can easily generalize to this general formula over here. So here is an example. Let this be the set of events A1, this the set of events A2, this the set of events A3. Clearly, there are no common members between A1, A2, A3. So, for example, it could be that A1 is the set of patients who have tested positive for COVID. A2 is the set of patients who have tested negative for COVID. And both A1 and A2 are young patients, but A3 are old patients. So here the sample space is entirely made up of three non-intersecting sets. They have no common members. These are young patients, these are also young patients, and these are old patients, but this is COVID positive and this is COVID negative. And so obviously we have no common members between any of the sets here. As the event B, I'll take patients who are on ventilator. In this yellow area over here, there are patients who are on ventilator. Now, they could be COVID plus patients, they could be COVID negative, or they could be old people. Now, actually looking at this picture, you can immediately see why Bayes' rule holds. So, let's look at A1. A1 is the set of all patients who have tested positive for COVID. There'll be a certain probability, and that will be P of A1. That's the P of A1 over here. There's a probability that those who have tested positive for COVID are on the ventilator, and so that is P of B given A1. And now that's over here. This is the probability of A1 intersection B. In other words, it's the probability of the events that lie within this area that I'm indicating with my cursor. Similarly, this over here is the probability of the events that lie within this part here. And finally, with n equal to 3, this over here will be the probability of events that lie within this region here. Now, these are three distinct non-overlapping sets, and therefore we can simply add the probabilities together. So add this to P of A3, and with n equal to 3 over here, of course. Now, this probability tree before you is really the explanation for Bayes' rule. So you see that there's the probability of A1 intersection B, which is this, and similarly for A2 and A3. And since these are all disjoint sets, so A1 intersection B was this, and so forth, then you can simply add the probabilities to get P of B. Now, knowing P of B, then obviously you know P of A1B, P of A2B, P of A3B, and now instead of 3, just generalize it to n. And therefore, it's clear why this statement that you see before you is correct. You're simply going to add the probabilities to get P of B, and well, this first part over here is really the definition of conditional probability. So that was the proof. Simple enough, wasn't it?